verify that f of x and g of x are inverses given f of x is 3x plus 4 and g of x equals x minus 4 over 3. So remember, to prove that they are inverses, you can put one function into the other one in place of x, and it should all work out to x. So if we were to take this 3x plus 4 and put it into the other equation for x, so we're doing g of 3x plus 4, which again, this means every time we see an x in the equation, we're going to replace it with 3x plus 4. I'm moving the equation all over the place so I can't even see it. So here's our only x. So that's where I'm going to put the 3x plus 4. 3x plus 4, and then we have the minus 4 over 3. Now if we simplify there, the 4 minus 4 cancel out, so we have 3x over 3, and 3x divided by 3 is just x. So that's all we wanted. There we go. They're inverses of each other. We're going to be given a graph. We're going to have to convert into the inverse coordinates there, and then we're going to graph it and see if it's a function. So looking at the first function points, 2, 6, 0, 1, negative 2, negative 4, we're going to find the inverse points of that, which again, you just flip the x and the y. So we'd have, oh my goodness. Technology, right? It's our best friend and our worst enemy. So we have 6, 2, 1, 0, and negative 4, negative 2. So if we were to come down and graph those points now, 6, 2, I can't even see the original. 1, 2, 3, 4, 5, 6, 2, 1, 0, and negative 4, negative 2. 1, 2, 3, 4, 1, 2. So if we were to draw a straight line through this ish, so the thing with if they are inverses of each other, they have to reflect over the line y equals x, which is just a diagonal line through the graph. And if you look, yeah, that's a perfect reflection on both sides. So yes, they are inverses of each other. And we'll talk domain and range some other time. I mean, this is a linear function, so it's all real numbers both ways. Now this one, we have negative 1, negative 4, so if we convert that to be negative 4, negative 1, negative 2, and 2.5, and 4, 2. So let's go ahead and plot those. Negative 4, negative 1, 1, 2, 3, 4, negative 1. We have negative 2, and negative 2.5 is about there. And then we have 4, 2, which is on that same thing. Weird. So let me draw my diagonal line here. So now if we connect these dots, I can't think of a way that we can connect them where they would be inverse functions of each other. Negative 4, negative 1, negative 2. Oh, it's positive 2.5 on that. That dot. Can I get that dot? There we go. Oh, goodness gracious. We'll do our new dots in black. Negative 2, 2.5 is up here. Okay. And then that'll swoop through there. Woo! So yeah, those are perfectly folded over onto each other. So they would be inverses of each other. My patience is exhausted for technology. I'm drawing all over the place here. All right, last one. And by the way, parabolas like this, they're not going to be inverse functions of each other. So if we were to flip this, we'd have 1, negative 2, 0, negative 3, and 1, negative 4. 1, negative 2. Down here, we have 0, negative 3 is there. And 1, negative 4. Oh shoot, this one does invert with the coordinates. Dang it. It's the formula one. We have to do the inverse formula of that. That one doesn't work out. Yep, so those are reflected over that y equals x. Fantastic. What else do we have? Write an inverse and graph both. Give the domain and range of both. So graphing x over 4 plus 2. If we were to write the inverse function for that, I guess we could just flip the coordinates. If we sub in negative 2 here for x, negative 2/4 is negative 1/2, plus 2, negative 0.5 plus 2 would be 1.5. So that coordinate would be negative 2 and 1.5. If we were to choose 1 to put in, or negative 1, negative 1/4 plus 2 would be 1.75. So we have negative 1, 1.75. Now these are going to be so close, we might want to pick ones that are further apart. If we chose 0, 0 over 4 is 0 plus 2 is 2. So we have 0, 2. Let's pick some larger numbers to reflect. If we were to pick 4, 4 over 4 is 1, plus 2 is 3. So we have 4, 3. And then let's pick like 8. 8 over 4 is 2, plus 2 is 4. So we have 8, 4. Now the inverse of those, you just flip the coordinates. So we would have 1.5, negative 2. We'd have 1.75, negative 1. We'd have 2, 0, 3, 4, and 4, 8. So we'll graph the first one in black, the second one in red. So let's see, 0, 2, 4, 3, 8, 4. 0, 2, 4, 3, 8, 4. Something like that. Now, remember, we're trying to see if this is reflected across this y equals x line, which is just a diagonal line through there. So if we flipped the coordinates, which I said we were going to do in red, we have 4, 8, 2, 4, 8. We have 3, 4, 1, 2, 3, 1, 2, 3, 4. We have 2, 0. We would have 1, negative 4. And those are perfectly reflected about that axis, that y equals x. So they are inverses of each other. If we were to come up with the equation, remember we flip the x and the y. X equals y over 4 plus 2, and then we solve it. So we would subtract the 2, and then we would multiply by 4, giving you 4x minus 8 equals y, but then we change it to f inverted x. So if you were to graph that in slope-intercept form, you would start at negative 8, and then you would go up 4 over 1. So it's down here, then up 4 over 1, up 4 over 1, up 4 over 1. It's almost easier to graph it in that linear form than it is to just pick the coordinates on something like that. So yes, because they are reflected, over y equals x, which again is just that diagonal line across the whole graph there. Oh, there we go.
There we go.